Okay, hi everyone. Thank you so much for joining the webinar. We will give it another minute just for others to join, and then we'll make a start.
Thanks, David.
Be settled on the believing now. Have a good meeting, everyone.
Okay, thank you. Just give it one more minute for others to join. Okay, well, let's make a start. So, good evening, everyone. Thank you very much for joining this evening's webinar. My name is David Pearson, and I'm the chair of the BCS Open Source Specialist Group. Delighted to have Ravi with us. I'll let him introduce himself in a minute. And of course, the focus of this particular webinar is going to be stream processing, particularly with a focus on the Apache Flink product. What we'll do this evening is I'm going to allow Ravi to present shortly. If you have any questions, we'll have a Q&A session after the presentation is concluded. Whilst Ravi's talking, if you also want to use the chat, I'll monitor that for any additional questions, and I'll hopefully read those out at the end as well as we move through the Q&A. So with that, Ravi, let me hand over to you. Let me, you can introduce yourself and go ahead with your presentation. Thank you.
Yep. Thanks, David. Hi, all. I'm Ravi. Today's webinar is on this open source distributed stream processing. First and foremost, I want to thank you all for joining this webinar because I realize it's at 7 p.m. in UK. For us, it's at 11 or here. So thanks for taking this, joining this webinar in a late evening. So today's discussion is on the distributed stream processing. So briefly about me, I'm an open source enthusiast. I have definitely grown with the community, being involved in multiple open source projects. I'm a committer and PMC to Apache Phoenix, which is a SQL layer on top of HBase. I'm also currently a technical lead on the streaming data platform at Lyft. For many of you who are not aware of Lyft, it's a ride-hailing company which operates in North America. It's second to Uber. So yeah, that's briefly about me. And we'll discuss around the agenda next. The webinar had a brief around what we'll be discussing, but this agenda here is more like we'll discuss around the stream processing foundations, Apache Flink community, that the whole Apache Software Foundation community as a whole, and how Apache Flink actually operates. And then we'll leave the last 10 minutes for a Q&A. That way, I'm happy to answer any questions that come in all throughout. So with that, let's go to the goals, meaning the key takeaway I want to share with this through this webinar is offer a brief high-level primitives and constructs around streaming. That way, you all have a fundamental understanding of the streaming concepts that usually all other stream processing frameworks usually have. And then also introduce Flink. I'll also give a brief overview of the trends that I do see happening of late, and then give around how ASF, which is Apache Software Foundation itself, operates. I wouldn't be diving deep into Flink, which means into the operations, the design patterns, and the best practices. That we could have as a different webinar. For now, we'll just keep it to the fundamentals. Also, I'll ensure that I'm not going to really discuss around all the stream processing frameworks and give a comparative study, because I haven't really worked on a lot of them. There are close to like 10 stream processing frameworks right now. But I'll just give a brief around the Flink and stream ecosystem, how they contrast with each other. So with that, I hope everybody's okay with all of this. I've just shared the goals and the non-goals. So uh, let's get started with the poll. I want to have a quick poll to just understand what best describes the experience you're having with stream processing. How many of you are very early beginners? How many of you have worked with it in a POC state, or are you using it in production? If you can type it in your chat, with one being a beginner, two being you just have done some POCs with it on any stream processing framework, and three is just you use it in production, just to get a pulse of it. Can you take a quick 10-15 seconds to just type it in your chat? One, two, three options. Okay.
So
A lot
mainly
of,
ones coming through.
yeah, I see a lot of ones. So this is good. Uh, Perfect audience, because I will be covering a lot of the streaming foundation. So I hope that the takeaway would be you get an understanding of the foundations and learn through it. So the fundamental question is, what is stream processing? And if one had to answer this, is like, you could call it as a data processing paradigm, where it's designed to continuously ingest, process, and analyze unbounded data streams. And if one has to just look at it from a pictorially, you have a stream of data that's coming in either from an IoT device or through clickstream, whatnot. You just have this continuous stream of data, and you would want to just start analyzing it in real time. So a stream is an indefinite one, meaning it doesn't really end at any point in time. So you just that's where it contrasts with a bounded stream, which you do for batch processing. So in a batch processing, you have your data available, and then you run a query against it, or you do some processing against it. But when it comes to stream processing, the data is just going to continuously come through, and then you have to process, analyze, ingest, and all of it. So that's where it slightly starts getting a lot of challenges with stream processing. And if you have to look into why one does stream processing, or what are the use cases for it, I want to just show this in a pictorial way. Like, a lot of organizations have moved into real-time processing, meaning in the last decade, we have seen a lot of a buzz around data is the new oil. But to make that into a reality, what organizations have really peaked into is to have real-time analytics, which entail, and primarily to do real-time analytics, stream processing play a big pivotal role in that. So that way you have real-time views, observations, and analysis on what's happening in your in your business. So there's always this, if you have to just put it in a chat, where you have time on the x-axis, and the business value of events that have happened in the last second, minute, or real time, has a higher value when compared to when you begin processing or analyzing that data after an hour, day, or months. And that the final tail of the spectrum is where you do a lot of these analytical use cases. Your batch processing comes in there, but it's in the first part of it where it's real time, or seconds, minutes, is where the greatest business value is there. And also stream processing kind of fits that very nicely for real time analysis. Like, if I had to take an example for anomaly detection in fraud, you would want to do it within the millisecond or a second, uh, since an event has happened, versus days or hours after. So also, like as I was saying, I work at Lyft, where there's a lot of it's a ride-hailing company. So you would do real-time dynamic pricing, where you would want to know what's the demand and supply at a particular location or a region in real time, which means you would want to know the weather. You want to know what's the current, is there an event happening, but you want to get all of that feeds processed in real time and try to react to it where you see a shortage of supply, you try to see how you could increase supply in those locations. So a lot of business value is derived from doing real-time analysis of all this data. And if you have to look into use cases, they gather. So you have IoT, where you would want to continuously monitor sensor data. You have logistics. Earlier, I worked at a startup which was into real-time supply chain management. And a lot of this shipment data used to come in from the carriers, and one wants to know at real time what's happening to shipments, whether they are on time, is there a delay, and all. And we used stream processing a lot to really get real time observability into systems. So also for network monitoring. So I think across the spectrum, we see a lot of use cases where having real-time processing and stream processing in a way really helps these big organizations to meet customer demands and add value to the customers. So with all this, kind of have convinced why we need to do stream processing and what stream processing is. I want to just go through the foundations of what stream processing is actually, and what we have seen over a period of time. And let's get into that. So the next section, what I would want to do is to give the foundational and speak about the few primitives that you would come across in various stream processing engines that you would be exposed to in future. And as I give that, I also want to take a journey back in history. And to do that, the way I would want to divide this, if you just look back in history, I would just try to break down into three generation of stream processing systems that have come in the last 20 odd years or 3 decades over. Everything before 2010, I've put in on categorized as the first generation. 2010 to 20 is the second and the third one. If you look at the first generation, there were a lot of data stream management systems that came out from the largest relational databases of the world, like Oracle, IBM, to just enable these real-time stream processing use cases. They kind of flipped the relational model itself, the databases, to support streaming use cases. And as we all know, relational algebra is very good for more like a batch process where you have the data in place, and then you run a query which determines what set of data to pick up as its input, and then it does the necessary execution of it. But when it comes to stream processing, the data is continuously coming in, and it becomes a huge challenge to really support streaming use cases on a relational algebra-based systems. And that's where the first generation of systems, what we have noticed or we see is they ran a lot of continuous queries on the data so that and create materialized views to serve the needs of streaming use cases. And in the first generation, a lot of primitives were not really well defined. So we saw these large enterprises coming up with their own solutions, but nothing like a common jargon that you could hear across. And one of the bigger challenges in the first generation was just handling out of order. A lot of these systems went ahead with processing the data as it comes, but as we all know, in a stream processing world where you're getting continuous data, there's always going to be network latency or any other factors that could influence how data arrives in the system. And these databases centric systems just couldn't figure out how to handle that gracefully. And while they really evolved, but I'm just categorizing them as the first gen. In this, I think once the Hadoop world where you started scaling out processing and data processing kind of became cheaper, storage and compute started disaggregating. we saw the next wave of stream processing systems. And a model that really stood out in this second gen has been the data flow model. This is something we'll discuss in the next few slides. There are primitives on how to handle out of order processing. What are the processing guarantees? Exactly once, at least one semantics. And in the first gen, a lot of systems, because they were scaled up, when you had a lot more data to consume and process, a, a solution that was adopted was load shedding. But now we see systems able to handle back pressure more seamlessly within it. And here we see a lot of systems like Storm, which came out from Twitter, Flink and Beam, Spark Streaming, Millville, again from Google. So a lot of open source projects also started building, few on the Hadoop ecosystem, few just outside. But I think Flink was a research project from a university in Germany, and then it was open source. So a lot of systems just or frameworks did evolve in the second generation. And now in this era, the third one is post 2020 onwards. You could say now we just have much a richer ecosystem, I would say, and we have moved beyond like a stream processing layer where you only analyze, like just analyze the data, and then you pass out the outputs to a downstream. But in the newer generations, now we see like a streaming databases, which just has the flavor of the first gen, where it gives you both the stream processing capabilities and also a database offering kind of a solution. And that's where we see the third gen, they're becoming more serverless. There's also convergence of batch and streaming. For a lot of the first and second generation systems, just viewed streaming separated out from batch. In the second gen, we heard a lot about Lambda architecture, and then came Kappa architecture. But now the newer generation frameworks and libraries just support batch and streaming much more uniformly. So yeah, this just break down the history of stream processing into these three layers. Next, as we discussed, I'll be zooming in more onto the second gen, which is the data flow model. Uh, and the primitives that really came out of that paper on the data flow model. So one thing in a stream processing system is the fact that there is this unbounded nature of the data. There's going to be out of order, which means unordered data set, which what that implies is the data that's generated, and by the time you process it, there's always going to be a chance that the data can come out of order. This happened very large number of times within Lyft, people from a phone, as you try to share the location of where the rider or driver is, the events could just, even though the app is just producing the result, the events, they just might come in out of order when it comes to processing. That's one challenge. The unbounded nature of the data itself was another big challenge. What solutions often came up that started off in the second generation just try to treat unbounded streams as bounded streams by just trying to break down a stream into fixed blocks and then try to process on top of it. So that really didn't fly well for a long period. So this model actually tries to address that.
Ravi, we can't see your slides.
Sorry?
We can't see the slides, the presentation.
Oh, that's interesting. Do you see that now, David?
We can see you, but not the slides.
Oh, that's interesting.
You want to try resharing?
Okay, I'll stop sharing and then try to reshare again. I'm sorry about that. Give me 1 second, David. I'll try to just address this. It does show that I'm sharing. Um, sorry, everyone. Ah. Can you see my screen, David?
I can see that now. Windows.
Okay.
Yes, I can see that. Yeah. Thank you. Sorry about that.
No, I'm sorry. Apologize, everyone. I'm not sure what happened. Okay, so we're discussing about the data flow, actually the data flow model. The thing I was just a quick recap, like um, the challenges of data flow in stream processing is this nature of that it's unbounded. The second part is the fact that data can come in out of order. And that brings up a unique challenge where how do you trade off between latency and correctness, which means as data is coming in, do you want to process it or do you want to wait with an assumption that the data that you currently have is out of order? And that trade-off has been a bit of a challenge when it comes to stream processing, and data flow model has kind of addressed this, has shared some heuristics to address this problem. And the third has been cost, where uh, with stream processing, there's always this infinite stream of data that's coming in. If you are to process it, there's always going to be cost involved. What's the effective way of handling that? So the paper which came out of Google is this data flow model, where it offers a practical approach to balancing correctness, latency, and cost. And one of the bigger push from this paper has been to just adapt and state that rather than trying to have try to treat unbounded streams as bounded streams and process it, just treat unbounded streams as they are, and then introduce the notion of time and state to effectively process it. So we'll go through the concept that have been raised in this paper. The first and foremost is Windows. So Windows allow a mechanism to actually break down your input slice of data, input stream of data into slices. So you could perform various kind of computations on top of that window. This looks similar to how we said, hey, why not we just break down into batches in the batch processing, but slightly differs where window is a first class primitive. Uh, Windows could be it will be time bound, where you could say in the last 1 hour, 1 minute, what has been the number of writes that have happened in a specific location. And that time-based ones is called windowing. So you could just group all the data which comes in that particular time period into that window. A window is created as soon as the first element that belongs to that specific window arrives, and is closed as and when the last event comes in, meaning it's more time bound here. And it offers a fine balance with correctness and latency, where all the data for a specific window, all the data for a specific time period is all grouped within a window, and then you process it. While you're doing continuous processing, it's just all part of that specific window. And the various kinds of windows, the first and foremost is like the tumbling window, where you define fixed duration buckets and they are non-overlapping, which means you could say every 5 minutes, I wanted a new window to be opened on my stream. So the data that comes in at 11:20 is going to go into the, and you have, say, for instance, for 5 minutes, it's going to start off at 11:20 and then end at 11:25. The data that comes in at 11:26 is going to be between the 11:25 to 11:30. So these are non-overlapping windows. And these are aligned. What that means is these windows are created on the entire stream. So all the data that comes in that period are going to be placed in that bucket, but again, internally grouped by a key. So that's where the alignment over here comes in. So for example, you have, say, for 5 minutes, every data that comes in between 12 and 12:05 is going to be in W1, 5 to 10 is going to be in W2, 10 to 15 is going to be in W3. So that's how the windows keep progressing. The next is on sliding windows. Here, it's still aligned, but there is an amount of overlapping between windows. So it's of a fixed duration, but overlapping. And the good thing over here is you could just start computing every minute, the last 5 minutes, how many writes have come. That could be a good use case. So what you're seeing is as time is progressing, your windows also start sliding forward, and then you're able to get much quicker results rather than in the tumbling one, you had the data that came in for 5 minutes at the end of the 5 minutes. Here, you could just say every minute I wanted last 5 minutes aggregations. You want to do some aggregations. That's where your sliding window kind of helps you in. So yeah, this is an example. Most of the systems, what happens is they copy the input record that's coming in into each and every window. So in this case, if you have a window length of 10 minutes and the hop of 5 minutes, that means every input data is almost copied over into two windows. And the copy is happening just for efficient computation. So yeah, you would see that behavior in systems. The third is the session windows, where these are unaligned. What that means is they are not defined at the entire stream, but rather on a per key basis. So if we could have a session to say that for every user who was logged in until they have logged out of my system, I would want to track all the changes that they're doing, and that this is where a window is going to be created the first time. Say I log in, my window is going to get created, and it's going to be expired based on some gap in when there's a period of time when there is no data coming into the system. So these are non-overlapping, and these are more specific at a per user level. So here, if my first event came in at 12, ended at 12:08, my window would close in at 12:13. And then again, the next one, assuming comes at 12:15, it just lasts for until 12:20, because assuming the last event that I got in that window is at somewhere around 12:17, something like that. So you see these non-overlapping windows, and these are unaligned. So what we saw right now is, though you have a stream, you're just able to break it logically into buckets. The next key thing that was defined in the paper is the time domain. And it's always, meaning time is one of the key primitive that needs to be well defined, and in a stream processing that becomes a key factor. As we know, like in any data processing systems, there are no guarantees that the events are going to come in order as and how they actually occurred. So if you take this example, just graph over here, if you just plot the event time and processing time, the dotted one is actually the ideal one, where you are able to process the data as soon as the event actually has occurred. But generally, that's not going to be the case. You just see this red line where you're going to process the data at a point later in time from when the event actually occurred. So there's always going to be that difference between the ideal thing and the reality, which is how the data is going to be processed. So this is where we have this two notions called event time and processing time. So the event time is on the event itself. You're going to get some timestamp to say that is when the actual event occurred. And processing time generally is when the machine is actually processing it. And that delta between the two is the skewness that likely happens because of the nature that there's going to be network latency and whatnot. A lot of the external factors can come into play. So one thing to note with time domain or time with event time and processing time is stream processors can support both. Many of the stream processing frameworks support both, but there is one key differentiator in terms of when to choose what. The key one is the deterministic nature in event time. So what happens is in real world, as you keep processing the data that arrives, uh, and say you wanted to compute how many users have checked in into your system for every 5 minutes. So if you go with processing time, it's always influenced by how quickly the processing engine is able to ingest data and process it, because that's going on the wall clock time. It really doesn't group the data that's coming into the respective time windows. It doesn't honor the time windows of the actual event, but rather it's primarily based on how or when it is processing the data. So this leads to a non-deterministic nature, where assuming you run the data, you run with the same set of data today, and then you run it again tomorrow for a historical date, what's going to happen is it's going to be influenced by how the job runs the next day if you use processing time. If you use event time, because of the fact that the windows are going to be created according to how the events in each event, the timestamp that event belongs to, that's going to be used to really determine which window that event belongs to. So what's going to happen is you're just going to get much more deterministic things. On the flip side, latency is a concern, because in processing time, you're just processing as quickly as you're getting the data. But with event time, because of the nature that there's an out of orderness, there is this notion that we're going to discuss around watermarks, which kind of build like these heuristics to say like the system is going to build these heuristics to say that it has seen the data until that point in time, and that introduces the latency. So there are these trade-offs between the two. Based on the use case, you could choose either event time processing based systems or event time or processing time based. So as we discussed, the data is not going to come in a timely order. So watermarks are the ones that this paper kind of has shared out to say the system should be able to generate watermarks which are more heuristic in nature, but allow the notion of time to be progressing as data is being processed. So if you see this, the same chart that we saw earlier, the red line marks the ID, meaning what the ID, not the ideal one, but how actually the time between event and processing time. You see this orange one that I've just introduced, that's going to be a watermark. You could just draw a watermark like that, meaning this is just a pictorial representation. What I'm trying to say here is watermarks are more heuristic in nature. They really don't represent the actual time, because of the fact that we just don't know when all the data has arrived from the producing systems. So we go with this heuristic approach. So at any point in time, a watermark T would indicate that all the data up till timestamp T is being processed by the system. And anything after that is up to how each framework would want to handle that. Some systems kind of drop the data. Some systems kind of give you retractions and additions, retraction support, which would allow you to get a call back when late data arrives. And this is the watermarks are the ones which give you this fine trade-off between latency and completeness, where you would not want to wait for too long for the watermarks to progress. And also you don't want it to be too fast, because that also yields to the lack of completeness, meaning you just are not sure when all the data has arrived. So there are multiple ways to run generate watermarks. Some systems support having like a delayed time wherein you say that, hey, I know that my system in my use case, all the data for 1 o'clock is going to be arrived with no later than 1 minute. So which means by 1/1, I should have all the data until 1. So in those cases, it's a configurable thing. You would say that, hey, I wanted my window to actually finish off at 1/1 rather than 1 o'clock. But this way, what happens is by giving that additional buffer, you're just handling the cases of out of order events. There are other statistical methods also. This like the paper recommends, but a lot of systems kind of go with the incoming data and then some notion of what the user would prefer to configure for their use case. So this is just an example. Okay, so the next one is triggers, where we have seen you're going to have the streams, you bucket them into windows, and then the event times help in determining in which bucket or a window should that event should be put into. And then the next is triggers. They determine when the window should actually end and what should be done at that point. So you could have event time based windows or triggers or processing time based. So in an event time, once the watermark passes beyond the window end time, then the trigger gets kicked in and the data for all that has been accumulated in that window is going to be processed. So 10 to 10:05, assuming that's the window, and you had like a watermark with a 1 minute out of orderness or lateness configuration, then at 10:06, the window for 10 to 10:05 would be materialized. Okay, the next is incremental processing. As we saw, watermarks are more heuristic in nature. They can either complete too fast or too slow. What the paper recommends is there should be the support for retractions and accumulations where either the delayed data is going to be sent back with the past state of the window along with the newer incoming data, which would allow downstream use cases to handle late arriving data. What that means is once the window expires, you're going to compute some aggregated value. And then if delayed data is coming in, the framework should be able to again pass a callback to the code to say that this is the late arriving data. What do you want to do? You either drop it or continue on. So this is the first set of like the paper actually recommends these kind of these primitives that you would see. And it treated windows and time as like these first class primitives and support for how to handle delayed events. Then there has been the second kind of phase of uh, research papers which talk about the materialized view model. And this is where you see a lot of these KSQL databases or the newer streaming database systems actually hooking onto this model where rather than actually giving a output or a result which is computed at a fixed point in time at the end of the window, these materialized views model approach is to incrementally reach to that end state. Now, what does that mean is you're going to run like continuous queries, and there are these shades of what we have seen in the first generation, where you have the data and then you start running continuous queries on top of the data, and the output of those queries are going to go to materialized views. So what this means is for every downstream use case, you would predefine the query, you would define all kinds of joins that you would want, and the stream processing layer internally would ingest the data and then determine which views should be updated with the latest data. So that's being taken care of. And here you see that it's all incremental, which means these are great for use cases where you want to see real-time analytics on top of as the data is just coming in. And it's a point in time accurate system where you run the query now, you're going to say you get one result for window from last 5 minutes to now, and then the next minute you're going to get a different result. But as I said, these are incremental in nature and they try to converge eventually at some point in time. There are some trade-offs in this, but if you have to just contrast quickly between the two, consistency is a big one. In a data flow model, you can get exactly once processing. Consistency guarantees are there, but in the materialized view, it's a point in time consistency where at that point, whatever is the data that's arrived is a value that gets returned back versus waiting for out of order and all of these use cases. Also, the usage is slightly different in a streaming one. It's more push based, where the stream processor is just going to process the data and then push the output. But in a materialized view, it's more pull based, where you're going to run queries on top of the data that's come in. But the queries are going to be much faster because it's all pre-computed. Yeah, so user-facing queries, typically we have seen just a huge set of use cases where teams want to do real-time user-facing queries. I've tried to go with this materialized view model. So that's that. With that, I've just kind of introduced the basic primitives in streaming. So the key takeaways are watermarks, windows, kinds of windows, the event time and processing time, and triggers. All of these might be aware, you all might have heard it in some shape and form, but at least the paper kind of puts it forward as to the recommended way of handling this unbounded streams. With this, I'll go to the next phase of the session I want to discuss, which is, I know we're running short on time, it's 11:40, so we'll go to Flink quickly. In the next 10 minutes or 12 minutes, I want to just try to give a quick overview of Flink. So Flink is actually a streaming framework and a distributed processing engine, which means it gives you both the API layer and the processing layer for stateful computation. The good part of Flink is while it started off as a pure stream processing engine, it's kind of matured to now offer both unbounded and bounded stream APIs so that you just do not need it only for stream, but also for both streaming and non-streaming use cases. So this is like a typical high-level architecture. You're going to have all these streams and historical data as your sources. You're going to build like a quick processing code. I'm going to show some examples of this, and then the output is these end systems where you want to publish the data out. It's been used by a lot of companies. I work at Lyft, and we have used it extensively for real-time machine learning, a lot of other use cases for ETL, streaming analytics, and a lot of other big companies have used and benefited from Flink. So the unique capabilities, if I would want to talk about, is this correctness guarantees. It offers an ability to give you exactly once processing, at least once processing. It has these notions of event time, processing time. It has this layered API where you can actually write SQL to simplify development. And you have these data streams API, and then the process function is just like going into the bare core API of Flink, where you handle state and timers uniquely by yourself, meaning as a developer. And the middle one is the stream and batch, is just this higher order abstraction where you're just going to, it simplifies with a simpler API. Performance, it offers like a under sub-millisecond latencies, given the fact that it's a continuous stream processing engine, where as the data arrives, it just flows through the entire graph of your pipeline from begin to end, where begin is your source and end is a sink. It also has high availability. That's where your scalability and operational part of it comes in. So for instance, assuming you have this program, I've taken Java here, but it's a very lightweight program. What happens is that code gets distributed by the framework, and the core set of things that you would see is your source, your series of transformations that you want to do on the data, and the final sinks. And what you can set is parallelism on your operators, and Flink takes care of trying to distribute the entire job graph onto this cluster of resources to process it. And all you define is just the simple code in the top, which is your stream, how you would want to handle that stream. Here, I'm just doing like a mapping function where I'm enriching the data, and then I want to distribute the data by an input key. And then I want to window it where I want to create a tumbling window of 5 seconds. And then the output should be going off to some output stream. So this is at a high level from a code to an execution part of it. And if I have to talk about the high level components, you have your Flink program, and then you have things like job manager and task manager. Job manager is the brain of a particular job, and all these interactions happen through the actor system. And the client, when they submit the code, goes to the job manager, that gets scheduled onto the task managers, which is where the actual execution of the code happens. And you could just scale out your task managers to get based on your load. You could just distribute it onto multiple task managers to execute the particular program. And a lot of these heartbeat messages and all get exchanged between task manager and job manager. And any task manager goes down, once they come back up, they kind of send the heartbeats to job manager. So you could say that the job manager has this role of resource management and job management, and also takes care of checkpoints, which is one of the most crucial thing, I would say, when stream processing to handle fault tolerance. We'll discuss about that. There are a lot of stateless and stateful operations within streaming. Things like map, flat map, where you just take in one input, produce another, is like a stateless operation. But a lot of stream processing frameworks offer these stateful operations where, like in cases of fraud, take an example, you get an input and you want to determine if it's fraud or not. A simple way could be that if it's over some threshold, you could have a use case or a rule to say that if it's above a threshold, it's marked as fraud. In that case, it's a stateless operation. You're just looking at one event at a time. But if you want to look at a pattern or have an complex event processing pattern to say if this, and this, then it's an fraud, then you want to have some state to be held. And Flink offers state as a top first class primitive again or here, which, unlike an external database or someplace where you'd have to make a round trip, you could just store it within Flink itself. And that's where you have the stateful operations, windowing, pattern matching, deduplication. A lot of these are stateful operations. So as we discussed, the data that comes in, you could put it in state for reusable purposes. So Flink supports two kind of pluggable state backends. One is memory, where you're going to put it in your task manager memory. And that way you just don't have any out of band communications. You can just make an API call internally to Flink, and Flink has the state stored in the manager's memory, and then it would just give back whatever you put in your state. So they're like this value state where you just can put in the last known value of a particular event. Say for instances, you would just want to know, hey, I want to know when was the last time this user logged into the system. That could be a value state, and that could be persisted for eternity. As long as the job is running, you would always know what's the last known state of a user was logged in. List state is you could just keep adding elements to that list, and then it can grow. One downside of in-memory state is definitely you are at the mercy of the Java GC. That can really cost challenges if you're going to go with memory size beyond like 60, 80 gigs. We've seen use cases where it goes way above that. But the alternative to that is RocksDB, which is more of a lightweight doc structure merge tree based system with more of a process which runs locally to the task manager, and then it just overflows to disk. So what we're discussing was on checkpoints, where as the state is being built up in a Flink job, where you're holding the state or the previous whatever data you want to have for use cases in your streaming, that needs to be persisted so that in the eventuality there is a failure, you would not want to lose that state. And given the fact that that state is local to your streaming job and not available in some external databases, you would want to have a way to preserve that data, right? So Flink has this checkpointing as a mechanism. It's been inspired by the Chandy Lamport's paper of taking asynchronous snapshots. What happens is at a scheduled intervals, the job manager is going to just kick in a checkpoint activity, and each of your operators in the JAG kind of takes in whatever data that's actually available at that point in time, writes it off to a persistent store, could be S3, could be HDFS. That data gets written off, and then that way, as it happens at some regular cadence, anytime the job fails, it gets back to the previous checkpoint, and then again, you're going to reprocess the data. This way, you're guaranteed that no, it also guarantees exactly once processing. It also ensures that no data is missed out in processing. So that's something of what we discuss in this failure recovery. And then one thing I want to talk about in watermarks in Flink is the watermarks flow from the you can treat a Flink job as like a DAG, which flows from the root to the leaf, and the root over here are your sources. So the watermarks get uh, kicked off from the source, and they flow through your job graph till they reach the sink. And at each point, each operator will always pick up the least timestamp of data that it has seen and then passes it downstream. Now, this is how all your windows and all get materialized as these watermarks flow through. I want to quickly, it offers SQL as a capability. So it's very quick to onboard and write streaming jobs, both batch and streaming using SQL. So they have these notions of tumbling end, tumbling start, hop end, hop start. So all the windowing capabilities we discussed, sliding, hopping, session, all of that is can be written as a SQL query. The other is it also supports incremental processing, where it treats stream and tables as a duality, where you could have, like, say, for instance, you have this query, which is you just want to compute the ID, name, and start time, where region like SFO, and then you want to compute it from the writes table, right stream of data, right? So what happens is you're going to get this continuous outputs generated from this query as it's running on an ongoing basis. So the SQL query gets converted into a job internally, and the output of that is actually sent out as meaning it produces the output, and then it goes into this table, like a internal structure that Flink has provided, and then the output comes in from that table. You could match the table to be like Kafka, you could match it to any external system, and that output is just going to be written off to that particular sink. It also supports these upstream and retract, where you can get like a change log behavior, where any changes, you not only get the inserted element, but also you get the previous state of it. And this supports like CDC use cases, where you get both what happened, what was the state before and after. Similar to how you get from SQL bin logs, you just get that capability also in stream processing with this. Integrations, there's just been Flink supports a wide variety of sources and sinks. Those are your connectors. It has a different library for CDC, where it allows you to actually uh, 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 tail the bin logs and all the other databases, and then have like these source connectors, which knows how to handle consuming data from these from these SQL databases, and then you get the streaming capability. This would be this is a huge win for all the ETL use cases where you want to get continuous streaming from databases to the offline store. Quickly on Flink and Stream, the biggest difference between the two, I would say, is the fact that Flink is streaming, and Spark streaming as just built as a batch system and then supported as at a micro batch level. What that implies is it kind of accumulates the data that it gets, and then passes that data in the state in a checkpoint kind of an offering, and then passes it along to the execution. Unlike a stream processing where the data continuously flows from top to the end, in Spark, the Spark streaming library just kind of has these RDDs where it first tried to batch the data and then send it across as micro batches. I've just listed down a couple of differences. I'll quickly go to, I've discussed trends, but I think I want to just spend the next 2 minutes on community. So as I said, Flink is an Apache open source framework. And for many of you, we all must have used Apache licensed or Apache based projects. And it's a big world's largest open source foundation. I think we all are aware of the Apache HTTP server, a lot of libraries in the big data ecosystem in Hadoop, the Kafkas of the world. All of those have just been part of this Apache software foundation. And in this, the key roles that you see is like a committer role, which because these are open source projects, while anybody can contribute to them, it's just committers have this ability to actually make merges to the code base. You could, like, developers could always raise pull requests, but it's actually the committers or a PMC member who can actually merge it. And PMC is just a larger, meaning a smaller group within committers who are actually responsible for making the high level decisions of the project. And you have like these release managers who actually shepherd releases. Flink has like 52 PMC, 117 committers. One can always get involved if all the stream processing that I've discussed today was exciting and you want to explore further. Apache Flink is one of the best stream processing framework out there. So the first and foremost would be joining the dev mailing, like dev or the user mailing list. Users is where you could just ask questions. Dev is you just also get discussions around the internal workings of Flink discussions. So that would be another mailing list you would want to join. The issues are tracked in that particular link I've shared, and this is all an open source, so you could feel free to look up the source code of Apache Flink in the GitHub repo. Flink team has done a fabulous job in trying to put up this link for contribution. So I think they welcome almost all these open source projects, at least under the Apache license in the ASF Foundation, do welcome contributions. So I think if any one of you are interested, please feel free to join them and look into how you can make your contributions. This moment, I promised 10 minutes, but unfortunately it's just 3 minutes, but I want to just open it up for questions. And before that, just one last thing. I think I want to also acknowledge and thank David for scheduling this. Thanks a lot, David. And then thank you all for attending. I'll open it up for questions now.
Yes, thanks, Ravi. Thank you very much for that. It was really interesting. Unfortunately, with the BCS meetings, they do tend to automatically end at the top of the hour, so we've got about 2 minutes left. If anyone has got any questions, please come off mute and we'll try and take them quickly. If we don't manage to get to you, then we'll carry on using our LinkedIn group, and I'll publish the replay of this hopefully in the next couple of days. And then if you have additional questions, we'll deal with that. So does anybody have any questions? Okay. I'm not seeing anything come through on the chat. Okay, I think we've got literally 1 minute left. So let me just say thank you very much for everyone attending. Thanks for your support for the BCS open source group. I've posted the web link in the chat. Please keep your eyes on the website. We are planning other sessions in the future and would love to see you back then. So thank you, everyone, and have a great evening.
Yeah, thank you all. Thank you all for attending. I know this is pretty late for you all. Truly appreciate your time to spend and listen to this at late hour. I will share the slides and I also shared my access in terms of LinkedIn and Twitter. So at any point, if there are any questions like you have at a later point in time, feel free to just drop and I'm happy to answer. Thank you.
But thank you very much, Ravi, for your presentation.
Yeah.
I'm going to end the call now. So thank you, everyone.
Thank you. Have a nice.
Thanks. Bye-bye.